Hi, it's Mr. Anderson and welcome to Biology Essentials video number 18. This is on positive and negative feedback loops. If you've ever driven, you've probably seen a sign like this. This is a gilt sign. So they put the speed limit up here and then they show how fast you're going down at the bottom. But you constantly get feedback as far as your speed goes. So you will see that you're going a little fast and so you'll slow down. But then you'll realize you're slowing down way too much and so then you'll speed up. And if it works out well, you'll hit that speed limit or that target set point. Now, what I'm just showing you here is what's called a negative feedback loop. In other words, you'll dance around that point. You'll speed up, you'll slow down, and eventually you hit that point. So a negative feedback loop brings you closer to the target set point. A positive feedback loop you would experience if you were to see this sign as a challenge. So you see you're going 30 miles an hour, so you realize I could go 39 or maybe 51. I could eventually get a ticket or break the sign. So that's a positive feedback loop. It's when you're amplifying and moving away from that target set point. So in this podcast, I'm going to start by talking about homeostasis, and that's our internal environment. And to maintain a stable internal environment, we use feedback loops. With each of those, you have a target set point. In a negative feedback loop, you're going to move above or below that, but try to stay as stabilized, and so you're as close to that as you possibly can be. Example I'll give you is temperature regulation in mammals. In a positive feedback loop, you move away from that target set point, so you amplify that. Example I'll give you is fruit ripening, why all the apples on a tree seem to ripen at the same exact time. Now, with a feedback loop, you can always have mistakes. You can always have alterations in that feedback loop, and that can lead to tragedy. Example would be diabetes is a problem in creating insulin or sensing that insulin. And so that's just a problem in a feedback loop, and it can lead to really bad things. And so let's start with homeostasis. Homeostasis, if we were to define what it is, it's an internal stable environment. And so if you live in a pond, if you're a paramecium like this and you live in a pond, you let a lot of your environment just go, and you maintain that environment by just maintaining the same as the pond around you. So you have this external pond, and whatever the temperature of that is, that's the temperature of the paramecium. Now, they'll regulate a few things like water concentration using contractile vacuoles, but mostly they have a pond. Now, as we move out of the pond, or as we become more sophisticated, we kind of bring that pond with us. That internal pond now is what homeostasis is. And so this is a hairless cat. Hairless cat is going to maintain its body temperature, and so it does that through feedback loops. It's going to maintain its blood glucose level. It does that through feedback loops. It's going to maintain the osmolarity of its blood. It does that through feedback loops. Now, hairless cat doesn't have hair, and so it's actually hard to maintain its internal body temperature, and so you don't want to let them go outside on their own. They'll lots of times put a coat on so they can maintain that. Now, there are kind of two life strategies. In this picture, it'll take you a second to figure out what it is. This is a snake eating a rat, and it's taken with a thermal image camera. And so the snake itself is what's called an ectotherm, and what that means is that their internal temperature is going to be the same as their external temperature. So the snake is about the same as, whatever the counter that it's sitting on. But the mouse is going to be an endotherm, and so that is going to keep an internal temperature that's going to be constant. Now, there's some advantages. If you keep an internal constant temperature, then all the metabolism will work at the same exact rate. The problem with that is that the rat right here is probably going to eat a lot more than that snake just to maintain that body temperature. So let's see how that works in a mammal. And so in humans, we use a negative feedback loop to maintain our constant body temperature. And so our constant body temperature is around 37 degrees or about 98.6 degrees Celsius. And so we use a negative feedback loop to maintain that. So let's say we put a thermometer in this kid's mouth and the temperature all of a sudden increases. Now, you actually sense that. The area where we sense that is on the roof of our mouth, in an area, an extension of the brain called the hypothalamus. And so we're going to sense that temperature change. And so what's the first thing that your body does when you start to get too hot is that you're going to sweat. And so what does that do? Well, as these water molecules evaporate, that's going to create evaporative cooling. In other words, they're going to carry a little bit of heat with them. You'll also start to vasodilate. In other words, the blood is going to be carried towards the surface of the skin. And so then just through convection, we're going to start to lose more of that heat to our environment. Now, another thing that would happen if we had fur, which we don't really have, is that fur is going to lay really flat. And the reason why is that then we can have more of that heat being lost through convection. So what does that do to our temperature? Well, it's going to drop. But it might drop a little bit too far. So then we're going to turn those things off. We're going to quit sweating and we're going to quit vasodilating. But now we're too cold. So what do? How do we keep ourselves warm? Well, we're going to start to maybe get goosebumps. And these are kind of crazy goosebumps. But we're going to get goosebumps right here. And what goosebumps do is if we had hair, it actually stand the hair up on end. But it also kind of pulls your skin in. It's like taking a coat and kind of pulling it in. And it's conserving that heat. We're also going to vasoconstrict. In other words, we're going to shut off those capillary shunts, and we're going to hold that blood in towards the inside of our body to maintain that. And as a result of that, we're going to have less convection, and our body is going to increase until we hit that target set point. And so right now, in fact, throughout the whole day, your body is just regulating your body temperature, and it's doing that through a negative feedback loop, again, trying to maintain that target set point. What happens if we want to go in the opposite direction? Well, let's say we have this. So we've got a fruit on a tree, and we call that the target set point. But let's say we want to move from fruit on a tree to fruit that is ripe. Now, why do trees make ripe fruit? I could talk about that for a long time. What they're essentially doing is making an attractant. So birds and humans are going to come and eat the apple and spread the seed somewhere else. But how do they maintain that? Well, they communicate, and it's kind of hard to understand how a plant could communicate, but they communicate through a plant hormone called ethylene. Ethylene is just C2H4, and it's given off by ripe fruit. In other words, this gas is going to be given off by ripe fruit. It's going to be picked up by apples next to it, and then it's going to cause them to ripen as well. And so if you take one nasty, over-ripened apple and put it in a barrel of apples that aren't ripe at all, they will all ripen as a result of that ethylene. And so one bad apple can really spoil the whole lot. But how is this an example of positive feedback? What goes on is that first apple will become ripe. And so it's going to start giving off ethylene. And that ethylene is going to be picked up by apples right next to it. And they're going to create more ethylene, which is going to create more ethylene, which is going to create more ethylene. And so through this positive feedback loop or amplification, all of a sudden all the fruit on the tree are ripe at the same exact time. Another famous example of positive feedback loop would be in childbirth. The pressure of the head on the cervix of the mother actually causes contractions, which pushes more pressure on the cervix, which causes more contractions, and so eventually the baby is born. And so usually we see positive feedbacks when we want something to happen really, really quickly. It's not something that we maintain for a long period of time. So what happens when something goes wrong, or what happens when there's a mistake? A great example of a feedback loop in us, so this is a negative feedback loop, would be blood glucose levels. And so the blood glucose level is the amount of glucose that's moving around the blood in your body. Where else could it be? That glucose could also be taken in by the cells so they can do respiration. We can get ATP from it. Or we could also store it in glycogen, which is mostly going to be found in the liver. And so we use two different hormones, insulin and glucagon, to do that. And so this is your pancreas. Pancreas is going to, its major job is to empty digestive enzymes into the small intestine when there's food there, and so we can break it. But they break it down or absorb that, digest and absorb it. But they also have a dual purpose, and one is to regulate the blood glucose level. And so they have two types of cells in here. They have beta cells and alpha cells. And so the beta cells and the alpha cells are they're just sensing the blood glucose level. And so this is an example of a beta cell right here. And so this is our glucose transport. It takes glucose in. This would be cellular respiration here. And so if we have a lot of blood glucose outside the cell, in a beta cell in the pancreas, that's going to trigger an influx of calcium, but more importantly, it's going to increase the amount of insulin that it's giving off. And so what that means is that when the blood glucose level is high, insulin, which I'll represent with this red kind of a dot, is going to be secreted from the pancreas. And that's going to move throughout your whole body. And it's going to trigger cells in your body to take in that blood glucose. And it's also going to tell your liver to store that as glycogen. And so when your blood glucose level goes too high, insulin is secreted, and that's going to cause your blood glucose level to go down. What happens when your blood glucose goes down, so dangerously down? Well, then your body is going to quit producing that insulin, and it's going to start producing glucagon. Glucagon is going to be created by the alpha cells in the pancreas. And so now when the blood glucose level goes too far down, glucagon is added, and that's going to increase the blood glucose level. In other words, it's going to free up glucose from glycogen in your liver. It's going to increase the blood glucose so you can actually use that throughout your body. Now let's actually see how this works throughout the day. So this would be in a typical person. What we've got here is the glucose levels in red, and so the glucose is going to increase, but it's increasing 3 times a day, and that's because you have breakfast, lunch, and dinner. But if you look at this dance, is like right next to it. This is this dance between the blood glucose level, which is red. As it goes up, the insulin level is going to increase as well. What does that insulin do? It causes the blood glucose to drop, and then we're going to increase insulin again. And so we get this cycle throughout the day of an increase in blood glucose, increase in insulin, and then we keep that at that level. And so if you look at it, our blood glucose levels throughout the day are going to maintain a fairly static kind of a position. Now, if we were to eat smaller meals throughout the day, that would probably help us keep that together. But what happens if we have a mistake? What if we have an alteration in this feedback loop? Let's say, for example, that you are type 1 diabetic. Type 1 diabetic, the problem with type 1 diabetics is that they have beta cells that don't work. So remember, the beta cells inside your pancreas are secreting that insulin. But if you have type 1 diabetes, or sometimes called that child onset diabetes, you have destroyed these cells. It's usually, there's a genetic component to it, but it's mostly an autoimmune disease where you destroy the beta cells. Well, what happens if you destroy the beta cells? Now we're going to have a feedback loop where the blood glucose comes up. There's no insulin to secrete, and so blood glucose keeps going up and going up and going up. And so your cells aren't going to take in that blood glucose, and so we have some nasty stuff that comes as a result of that. And so here are some things that happen. Increases the blood pressure, can eventually affect the eyes. You have nausea, vomiting. A lot of the ones in blue here are for type 1 diabetics, but it eventually can lead to putting you in a coma or actually death. So if you're a type 1 diabetic, that's just a mistake in the beta cells in the pancreas, so we can't make insulin. If you're type 2 diabetic, that essentially means that you've had too much glucose throughout your whole life. It usually is tied to lack of exercise, obesity, things like that. Type 2 diabetics, the cells in your body just stop recognizing that insulin, and as a result, they quit taking it in. And so how could we solve that problem knowing what you now know? Well, if you were to get insulin shots, like an insulin shot right here, or an insulin shot right here, or an insulin shot right here, and insulin, I think, was first synthesized or created in the 1920s, but now we make it through molecular biology. But if you could get insulin shots throughout the day, then you can regulate that blood glucose. Or now they use a insulin pump, which is going to administer different amounts of insulin throughout the day, so it works almost as a feedback loop. Now, this is a map of where diabetes is on our planet. About 3% of the people in the U.S. have, or worldwide, have diabetes, but about 90 to 95% of that is not a mistake in the beta cells. It's actually tied to our diet, type 2 diabetes. And this is a chronic disease. Once you get diabetes, you have it for the rest of your life. And if you look here, where are we seeing the greatest incidence of diabetes? It's just tied to our diet. And so we're eating a high fat diet, and as a result of that, the diabetes, a high sugar diet, corn syrup diet, and as a result of that, we're getting huge diabetic increases. But the whole thing is tied to a mistake in a feedback loop. And so that's feedback loops, positive and feedback, positive and negative, and so I hope that's helpful.